Welcome back to STEM Online Academy. My name is Jason Masterakos. For those of you who don't know about the channel, for those of you who do know me, you've probably noticed something interesting last week. I am now discussing what my brand and services are, how they can help you, the audience, and our approach to rigorous problem solving in advanced mathematics and physics. Okay, so from now on, we're going to go back and forth. There's going to be uh, a day where I'm going to be discussing strategies and techniques and systems, rigorous systems on how to solve a lot of these complex problems. And the other day, we'll just go back to the usual me on the whiteboard solving uh, the types of problems that come up on either midterms or exams, but specifically the really hard problems. Okay, so that's going to be my style from now on. I think it will be the most effective, and why you, the viewer, uh, why you should like and subscribe, and or inquire about our advanced coaching services. Okay, so today we're going to be discussing an interesting concept. I'm going to go back because remember we rotate back and forth from mathematics to physics. We're going to talk about something interesting here. We're going to talk about a particle in a box. Okay. Now, you may be asking, what the hell do I mean? Particle in a box. That's exactly what I mean. Particle in a box. So this is we've talked a little bit. I've done some videos on um, some of the introductory stuff in quantum physics. Okay, and this is one of them. Okay, we're going to be looking at something called a time-independent Schrodinger equation. Okay, so a time-independent Schrodinger equation. Okay, and we're going to specifically look at this question. What it means by time-independent is means that uh, the wave function c of x, right, is independent of time, right? So there's no time parameter. It's just a function of one variable of the position. Okay, so for those of you who have seen this type of equation before. Well, this is a specific question, but there's a specific formula. It's usually written something like this, but it has the energy or potential energy inside of the equation. Okay, so we're going to look at a very interesting equation. Okay, it's called the time-independent Schrodinger equation. Okay, and it's a differential equation. That's why I want to bring it up. Okay, it's a specific ODE, which our channel spends a lot of time doing. Okay, so let's look at how we're going to solve this. Okay, so we want to solve this guy here. This guy will be solved by doing the following. Okay, so how are we going to do the solution to this? Okay, so let me just get my pen out. All right, so solution. Second here. Always have to get a new pen, guys. All right, so for the solution to this, okay, what we are going to do is we're going to do the following. Okay, what type of ordinary differential equation is this? That's what we have to ask ourselves. Okay, because you'll notice it's an ordinary differential equation. Even if you haven't done quantum physics before, if you understand ordinary differential equations, then you'll be able to solve this problem. Okay, you don't need to know the physics per se, but if you understand the mathematics, that's pretty much all you need for this. Actually, this is purely a mathematical problem. Okay, so we're going to start the time-independent Schrodinger equation. Okay, and this specific equation I have here is actually inside the box. Okay, so inside a box, when it's inside the box, okay, the potential energy actually goes to zero. That's why it's written like this. For those of you who've taken quantum physics, you'll probably say, where is that energy constant? The energy constant's not there because we're inside the box. So the potential energy is zero. So we're dealing with this. Now, outside the box, the potential energy would have been infinite, okay? And that means that the particle is strictly confined between x equals 0. Okay, so we need to write some constraints. Okay, so before I write the solution, so I'm going to write something here, right? So inside the box, so inside So 1 second. Inside the box. Inside the box. Inside the box, potential energy, right? Potential potential energy is 0. Okay. So inside the box, the potential energy, it goes to 0, right? Is 0. Is 0. That's one of the things we need to know. Now, if we were outside the box, right? So outside the box, outside the box, okay, the potential energy becomes infinite, right? So potential energy, potential, just 1 second, potential energy is infinite, okay? This means that the particle is confined, okay? So the particle in the box is confined to have the following, okay? So that means particle, um, particle has to be confined, right? Is strictly confined between between the constraints x equals 0. Okay, so x equals 0 and x equals L. Okay, that's what you have to understand here. And what we have, that means automatically the boundary conditions. Okay, so this means the boundary conditions. Okay, this means that the boundary conditions, the boundary conditions okay, are the following. Okay, it means that we have the following boundary conditions. Uh, C of 0 is equal to 0. Okay, and C as a function of L, where L is you can say the length of the box, L is equal to 0. Okay, so I need to correct myself a little bit here. Is the fact that you need to know these boundary conditions with that differential equation that I was talking about up here in order to solve it. Okay, and the only way to know these boundary conditions is that you need to know, yeah, you do need to have a little bit of that physical intuition of how to get these parameters. But now, if you have a background in ordinary differential equations, you can solve it. Okay, right? Because now we have our differential equation, the time-independent Schrodinger equation above, and our boundary conditions, C of 0 and C of L. Okay. So what is the real mistake that most students have when it comes to problems like this? And so what's the issue? So most students will make the error. Okay, so let me just go to another page here. Go to another page. Okay, the real mistake. Okay, so let me just put over here, real mistake. Right, so the real mistake that students are making. Okay, right, the real mistake. Most students are going to make this error. Okay, I'm just going to write it below. Okay, so most students are going to make the following error. They jump directly and make assumptions such that c as a function of x. By the way, if you don't know what c is the defined as the wave function. So c as a function of x is equal to capital A, the amplitude, times sine as a function of the wave number times the position. Okay. And okay, yes, mathematically it looks nice. And you come to this, but the problem is not the mathematics. The problem is understanding why, like what it means. Okay, and that's the big problem when it comes to uh, quantum mechanics, is that if you don't understand the okay, you may understand the mathematics, but if you don't understand how the physical system interacts and works, you may have a problem. Okay, so just memorizing the answer or memorizing the solution doesn't give you anything. Okay, not to say that memories are important, but just memorizing it is not going to give you anything in terms of the meaning. Okay, so they don't understand why cosine disappears. They don't understand why the cosine is disappearing here, and they don't understand where the quantization is coming from. Okay, and because of that, it never feels stable. Okay, so in this video, I'm going to fix that mistake properly. Okay, so let's start with a clean mathematical reset. Okay, so let's start with, so I'm going to go over here now. Let's go to having some sort of solution, or let's do a solution to the following. Okay, so solution, smart step. Okay, so I'm going to make a solution, so approach to the solution. Okay, so let's do a clean mathematical reset. Okay, so first we're going to rewrite the equation in simpler form. Okay, remember what the equation was. Time independent Schrodinger equation was negative h bar squared over 2m, negative h bar squared over 2m. If you don't know, h bar is Planck's constant, m is the mass. Okay, times c double prime of x. C is the wave function of the particle. Double prime is, you should know that mathematically, that's just a second derivative as a function of the position. And this is equal to the energy times the wave function as a function of the position. Okay. Now, if we multiply both sides by negative 2m over h bar squared, you'll notice that we're going to get something like this. Okay. We get psi double prime plus k squared, right? Just 1 second here. K squared times psi equals 0. Psi or psi, you can call it. Okay. Where now, what is k? I have to define what k is. Okay. I'm going to put here k, okay, where k is equal to 2 times the mass times the energy divided by Planck's constant squared, h bar squared. Okay. I just replaced the k with that. Okay? Just to make it more condensed, our differential equation a little more condensed, so we don't have to deal with it. This is not a quantum equation anymore. Okay? You'll notice that this is just a second order linear homogeneous ODE with constant coefficients. And you've solved this before. You must have in your differential equations classes. Okay. Now, the general solution to this, we already put it in auxiliary form. Okay. You will know that we're going to get this, right? General solution c as a function of x is equal to c1, right? C1 cosine of kx. Okay, so kx plus c2 sine of kx. Okay, this is the general solution to the auxiliary guy over here. I'm highlighting in green, auxiliary differential equation, whose solution to the auxiliary differential equation is a complex number. This is the solution to it. Okay, so this is general solution. Right, so this is the general solution. General solution. Okay. No shortcuts and no guessing. This is the full solution space. And now we're going to apply some interesting structure, right? First, we're going to impose one of the first boundary conditions, okay? We go back here in yellow, those are my boundary conditions, okay? So we have to employ boundary conditions, okay? So now boundary conditions, okay? Let's highlight here, put this first boundary. So I'm going to say here, first boundary condition, okay? First boundary condition, right? Okay, I'm just going to erase here. Okay, so the first boundary condition I'm going to start applying is C of 0 is equal to 0. Okay, so C, so I'm putting C of 0 is equal to 0. I substitute, I'm going to substitute this in now. Okay, so first boundary condition. Right, so substitute. Just 1 second. Time to get a new pen, I think. Substitute. I'm going to substitute C of 0 in. And you're going to notice that we're going to get this, right? We're going to get C. Let me move some of my stuff around here. Okay, just 1 second. So we're going to have C of 0, okay, is equal to C1 cosine, okay, cosine of 0 plus C2 sine of 0. Okay, that's what we're going to have right now. All right, and then you're going to see from here that we're going to C of 0, 0, just plug in the boundary condition. This is going to be equal to C1 C1 times 1, cos 0 is 1, C2 is 0, sine 0, 0, so plus C2 of 0. Hopefully you can see what I have down there. I'm going to go to another page. Okay, so let's do another page here. Need a new page. Okay, what you have noticed is that we've gotten the following. Now we have, remember, C of 0, right? So 1 second. It's my eraser. C of 0. Just 1 second, guys. Yes, C of 0. C of 0 we know was 0, okay? So since C of 0 is equal to 0, we had 0, right? Left-hand side is equal to C1 times 1 plus C2 constant by 0. This leaves us with 0 is equal to C1. So we now know what our constant coefficient C1 is, okay? To satisfy the boundary condition. Now, cosine didn't actually fail, okay? It was just eliminated by pure mathematical deduction, okay? And that is the key difference, okay? If we substitute C1 is equal to 0 back in to this guy over here, okay? C1 is equal to 0. Now we have a logical reason as to why that C2 sine kx approaches, or you can call C2a, right? I used a above, it doesn't matter, right? So now the wave function, right? The wave function psi of x. So I'm going to say now, so we have, so now, the wave function, the wave function. Now the wave function is going to become the following. C as a function of x is equal to C2 sine kx. So the assumptions that most students make, yes, it's correct, but it's correct by guessing, which is a problem. Okay, you don't want your solution to be based on speculation. You want to be able to prove and verify that it's correct due to reasoning. Okay, so like this is C as function of x. Okay, that's not a guess, that's a consequence, and that's what matters. Okay, So let's, we figured out one of the boundary conditions. You have to use both boundary conditions for differential equations. We will do the second boundary condition. Okay, so now I'm going to talk about the second. So second boundary condition, right? Boundary condition. Okay, let's go through this. Okay, now the second boundary condition is going to be using C of L. Okay, so C function of L. That L is when position X is equal to length L. So I'm inputting it into the function of C, and this is equal to 0. So C of L is equal to 0. That's the second boundary condition. I'm going to substitute. Right, so substitute. Okay, we're going to substitute into the guy there, right? Right, so we had C of L. So now we're going to have C of L, right? When X equals L is equal to C2 sine of K. L, for every position X, I'm inputting length L of the box, okay? The particle in the box. Okay, so now we have that. That means that 0 is equal to C2 sine KL. Okay, so I have sine KL. I can simplify that equation. Automatically, you should be thinking that sine, if I divide both sides by C2, I get sine KL is equal to 0. Okay. Now, I want to be able to solve this, right? Here is the critical thinking moment that you guys need to be utilizing. Okay, I'm going to write down here, right? And that is, okay, so either, right? Let's put this maybe, we'll put it in red. Either, so take note of what I'm saying here. Okay, so either you're going to have the following, okay? So either you're going to have B equal to, I'm sorry, C2 is equal to 0, equals 0, which gives us a trivial, makes you understand what I mean by CT being 0. That means that it's a trivial solution, right? Solution. Okay, so I have that. And or you have number 2, right? You have number 2, which states that sine as a function of KL is equal to 0. Okay? We need to reject the trivial solution. Okay, so reject trivial solution. Okay, so reject, obviously, reject trivial solution. You have to. If you do not reject the trivial solution, you're going to be wrong big time. You can't just assume that C2 is 0 and that's it. No. We're solving a time-independent Schrodinger equation. We want to solve it. And what I mean by solve it, we want to figure out an equation for the energy. Yeah, okay. So we require that sine KL, right? So we require that sine KL is equal to 0. Okay. But when does it equal to 0? Well, when does it equal to 0? Basic trigonometry will tell us that KL has to equal to n pi, where n is equal to 1, 2, 3, and so forth. Right? So where n is equal, and I'm going to be very specific about this, okay? Where there exists an n, right? So there exists a little n belonging to the integers, okay? I should be saying that to be mathematically precise, actually. Yeah, there exists an n belonging to the integers where n is equal to 1, 2, 3, comma, da, 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 okay? So for a particle in a box, we need to reject trivial solution, take sine KL equal to 0, and I'm getting that KL equal to n pi because I want to solve for KL by inversing the sign. So if I inverse sine, the only way to get sine inverse of 0 is to have multiple integers of p or multiple integers of pi, right? Because that's the only time when sine KL is 0. Okay. And that's it, right? You're going to notice quantization is forced by what? It's forced by geometry, actually, which is interesting. Okay, as you can see here, because we're using trigonometry to solve this. And it's not declared by physical speculations, right? A lot of you are using physical speculation to assume a mathematical solution because you were given a formula in your classes. Okay, yeah, the formula, but that's not good enough. Okay, here I'm proving it mathematically of how we get to that assumption in the first place. So no physical speculation and purely mathematical rigor. Okay, so let's go to the next part, right, where the energy quantization is coming from. Okay, right, so energy quantization. Okay, let's do energy quantization now. So energy, energy quantization. Okay. Quantization. This is the fun part. All this is fun. Okay, where the energy quantization is coming from. Remember what I defined earlier. I said that K, right? I said, what is K? You should know what this is. K squared was defined to be 2 times the mass times the energy divided by Planck's constant squared. Okay. Now, K itself was n pi, would be n pi over L. How do I know that? From this guy over here, I'm just rearranging for K. Okay, so we enter K again, n pi over L. And if K is n pi over L, I can substitute into K squared equals 2me over 8 bar squared, right? So this now becomes squared, and this is equal to 2 times the mass times the energy divided by Planck's constant squared, okay? Distributing the exponent inside mathematically will give us n squared pi squared over L squared. This is equal to 2 times the mass times the energy divided by 8 bar squared. Okay, 8 bar squared. I'm solving for energy, so multiply both sides by 8 bar squared over 2m. So now I'm getting n squared pi squared 8 bar squared all over 2 2m 2m l 2m l squared equals e. Okay, and that's what we get. We found the solution to our energy. Okay, so we derived the energy equation for a particle in a box, right? You've probably seen this in your high school classes or a very elementary modern physics class, but you've probably never seen it being derived before. Okay, so I'm going to put here, we figured out that the energy is equal to n squared pi squared 8 bar squared divided by 2ml squared. Note that n is equal to 1, 2, 3, and so on. Okay, so on. Okay, and let's see. And you can, and now you see it. So the energy levels are not just imposed. Okay, they emerge from boundary constraints. So I think that was a very interesting approach. Instead of memorizing a particular energy formula that you guys are used to, particle in a box, I derived it. There's much more value in deriving and verifying something than just remembering a result. So let's look at the physical interpretation. Imagine a string fixed at both sides, right? So if you had a physical interpretation, it is fast, right? So physical interpretations. pardon me for my spelling. Interpretation. I think if you're a math guy and the spelling doesn't come well, probably some of you can relate. Okay, so we have a physical interpretation that I want to be looking at. So what do I mean? Let's say you have a string fixed at both ends. Okay, so let's say I have boundaries here. Okay, boundaries here. And let's say I have a string fixed at both ends. Okay, so let's say for instance, here's my string and it's fixed at both ends. Okay, something like that. We have one wavefront and maybe another one. Okay, something like this. All right, to be accurate. Only certain standing waves will survive. And why is this? Why do certain standing waves survive? Because the endpoints must be zero. Okay, and a quantum particle behaves exactly the same way. If you have a quantum particle traveling along these wavefronts, let's say it's located over here, and then it moves, so forth. Or maybe it's over down here. Maybe it started here, and then after it's just going like this. Okay, right? The particle will behave exactly the same way. Okay, and the wave function must vanish at infinite potential walls. That's what these are. They're walls. Okay, so infinite potential, infinite potential walls. You'll know what I mean if you took a modern physics class. Infinite potential walls. So only certain wavelengths fit, and the energy is proportional to k squared, as I've shown you mathematically. And k is constrained by geometry. Now it's really geometric, if you've noticed what I'm doing. That's just structure, right? So if this topic ever felt overwhelming, okay, I don't know if it did for you guys. I hope you gained value from this. It's not because it's hard, it's because it's often rushed. Professors assume you're comfortable with, you know what they assume? And this goes for any program actually. They assume right when you come into a class that you already know second order ordinary differential equations, okay? Even though maybe mathematically you haven't learned them in your math classes. Boundary value problems, trigonometric structures. If any of those felt shaky, the whole thing collapses and emotionally you're in a rut. But mathematically, right? It's clean. It has a form of beauty to it. Okay. Right. So the mistake was, right? Remember what I told you what the mistake is, right? The mistake was, right? The mistake was thinking quantization was a physics trick, that it just comes out of some sort of magic wand and hand wavy arguments, which is nonsense. Okay. It's not. It's a consequence of ODE structure, ordinary differential equations. So ordinary differential equations. Okay, and boundary constraints that we've been using. Yeah, the first page, boundary constraints here. See those constraints at the bottom? Okay. That's the mindset shift. And that shift changes how you approach harmonic oscillators, will help hydrogen atoms, Fourier series, Sturm-Liouville problems. This is all foundational stuff. So if you are preparing for a quantum midterm, a physics final, a graduate level coursework, this topic should now feel stable, not magical, not hand wavy, but solid. And stability is what protects your grade. Okay. If this explanation, sorry, brought clarity to you, you'll find way more on this channel. I focus on the exact pinpoints where students, uh, where strong students quite often struggle. And if you want structure, calm, and focused guidance, my book and um, tutoring / consulting information are in the description below for this YouTube video. Serious undergraduates only. Okay, I mean serious. Well, obviously, you must be serious if you're doing stuff like this. Okay. So this wasn't about just solving an equation. it was about understanding why the equation behaves this way. And once you understand that, quantum mechanics becomes structured, not intimidating, and not scary. All right. Hopefully, if you're new to this, I want you to like and subscribe. Have any comments, please post them in the chat below. And as I said, my schedule is Tuesdays, Wednesdays, and Thursdays. I will be posting. I will be going back and forth from now on from problem solving, the advanced problem solving questions that we take up on this channel, and another day we'll rotate back to something else. I'm going to be talking about specifically techniques, not the problems, but techniques on how to solve advanced problems in mathematics and physics. Okay. Like and subscribe, please. It really helps. I'll see you in the next one.